Alright guys, welcome to lesson 5.10. We are going to continue our task of comparing the graphs of f prime and f double prime. So yesterday, or in our last lesson I should say, we started with the graph of f and we sketched graphs of f prime and f double prime. Today we're doing the opposite. We're going to start with graphs of f prime or f double prime, and we're going to see if we can sketch a graph of f from that. Before we begin, let's write down some helpful facts here. And in fact, I would encourage you guys to see if you could pause the video here for a minute and see if you could fill in these blanks. And when you unpause it, I will go over them with you. All right, so to begin with, if f prime is positive, that means that the slope of f is positive. So if f prime is positive, then f is increasing. And that means that it's going in an upward direction. Okay? Next, if f prime is negative, then f is decreasing, which means that it's going in a downward direction. If f prime is 0, then f is neither increasing or decreasing, because 0 is neither positive nor negative, right? So what would the graph look like if it was neither increasing or decreasing? Well, it would have a horizontal tangent line that is flat, right? Instead of going up, instead of going down, it's going to have a horizontal tangent line that is flat. Okay, so those little facts are going to come in handy on our examples that we're looking at today. All right, so let's go ahead and do example 1. Use the graph of f prime to sketch a graph of f. So given the following graph of f prime, I think maybe I'll put f prime up here instead, and I'll just use a different color to indicate that this is the line we care about. All right, there we go. So given that graph of f prime, our goal is to sketch a graph of f. Okay, well, what do we know about f prime here? What do we know about f prime? Well, now usually the best way to answer this question is just by asking, is it positive, is it negative, or is it 0? Okay, and in this case, if it's above the x-axis, it's positive. If it's below the x-axis, it's negative, and if it's on the x-axis, then it's 0. So in this case, this red line is above the x-axis, and therefore my derivative is positive. So the answer to this question is f prime is positive. And what did we say on the last slide? We said that if f prime is positive, that means something about f. So what does this mean about f? If f prime is positive, then f is increasing, we said on the last slide. Oops. And so my graph would look like a line that's constantly going in an upward direction. Because since this graph over here, since f prime is always positive, f will always be increasing, and therefore it will just look like a line that's going up. Now we don't know where that line is, okay? So the line could actually be up here instead. Or the line could be down here. We don't know. All we know is that f is increasing. We don't know anything about its initial conditions. This is, when you remember when we talked about in Unit 2, if you want to turn a derivative into a normal function, what do you have to do? You have to integrate it. But when you integrate it, you get a plus c, which is an initial condition, which tells you where that line is located. Okay, so we don't know how high up these graphs are because we don't have any initial conditions. All we know is something about their slope. So since the slope is positive, this graph has an upward bend to it. Now you can get more specific. Instead of saying, what do we know about f prime? Oh, well, it's positive. You could say f prime is always 4. I mean, look at the graph. It's at y equals 4. So f prime is always 4. So what does that mean about f? F's slope is always 4. So it doesn't, once again, it doesn't really matter where you start. You could start anywhere you want because we don't know where the starting point is. So let's just say I start here in the origin. Its slope is always 4. So over 1, up 4. Over 1, up 4. So now we can actually get a little bit more specific and draw something that has an actual steepness to it that accurately matches the graph. Now, for most cases, just doing this is sufficient, but every once in a while it is helpful to look at it in a little bit more detail. Okay? So now I want you guys to notice how I did this. The first thing I did was, how do we know if f, what do we know about f prime? And the question is it positive, negative, or 0? In other words, above, below, or on the x-axis. The next thing I do is ask, therefore, what does that tell us about f? And we had that little chart at the beginning of class to answer that. And from there, you make your sketch. So, 3-step process. 1, 2, 3. Right? So I'm going to go ahead and let you guys try one of these. I'm going to give you 2 problems. These are 2 separate problems. I'm giving you f prime twice, and you're going to write, therefore you're going to have 2 answers. All right. There you guys go. Go ahead and pause the video here and give it a try. When you unpause it, you'll see my solutions. All right, so here are my solutions. So what do we know about f prime in this case? Well, we know that it's constantly -2. So we have a constantly negative slope. So what does that mean about f? That means f is constantly decreasing. So we know our line goes in a downward direction. Now I chose to be more specific and say, okay, well, since f prime is always -2, I went ahead and did my over 1 down 2 to get the steepness correct. But you didn't have to be that specific necessarily. But I'm doing that on purpose because there's some problems we'll be getting to a little bit later that doing so might be helpful. All right, let's go ahead and take a look at part B. Now, in part B, what do we know about f? Well, we know that it's constantly 0 because it's on the x-axis. Since it's constantly 0, that means that f has a flat slope all the time. And so f looks like a horizontal line. It doesn't matter if you put it above or below because we don't, like I told you, we don't know the height of these functions. We only know their slopes. So I chose to put it up there, but maybe you put it down below. Or maybe you even put it right on the x-axis. It doesn't matter. So long as your answer was a flat horizontal line, then you've done it correctly. All right, let's go ahead and do another example. Okay, so here's our given graph of f prime. Our job is to sketch a graph of f. All right. So once again, let's start with our first question. What do I know about f prime? Well, I see that from 2 on into infinity, that f prime is positive. I also see that from 2 to the left, f prime is negative. And finally, I see that at this point right here, f prime equals 0 because it's right on the x-axis. So for the gray area, f prime is positive because it's above the x-axis. For the green area, f prime is negative because it's below the x-axis. And the reddish color there, the f prime is right on the x-axis, which means that f prime equals 0. So if I wanted to sketch a graph of this, how would we do it? Well, what does that mean about f? So that's question 2. Question 1, what do we know about f prime? Question 2, what does that tell us about f? Well, if f prime is positive from x equals 2 into infinity, then that means I'm going to go over 2 here. I'm going to go over 2, and I'm going to give it a positive slope starting at 2. Now, once again, the height doesn't matter. It could be there, it could be there, it could be there. It really doesn't matter where you choose to draw it, just so long as you know that starting at 2, we have a positive slope. We also see that f has a negative slope from to the left of 2. F prime is negative to the left of 2. Therefore, what does that tell us about f? That tells us that f has a negative slope to the left of 2. Now, this is still not quite right because it looks like an absolute value function, but it's not supposed to be. We'll talk about why that is in a second, but for now, just bear with me. We also know that f prime is 0 right here, so we know that there's a flat slope here. Okay, now a cusp is not a flat slope. So how can I get this to have a flat slope there? Well, what we're going to do is we're going to have to draw this graph a little bit different so that we still have a negative slope to the left, and a positive slope to the right. But we want a smooth turn down here so that we have a flat horizontal tangent line. Okay, so f would look like a parabola in this case. Now, how did I know that, though? I mean, well, I guess the fact that it equals 0 is kind of helpful, you know. But, you know, if I were to put some y values here, you know, here f prime is 4, 3, 2, 1. 4, 3, 2, 1. So here the derivative is 4, which means that you have a steep line. Here the derivative is 3, which means it's a little less steep. Here the derivative is 2, which means it's even less steep. Here the derivative is 1, which is even less steep. So if you have a steep slope and then a slightly less steep slope followed by a slightly less steep slope, and eventually you reach 0, right? Because that's what's happening here. Then, as you guys can see, it's not going to be a straight line like I drew it initially. It's actually going to be steep, less steep, less steep, less steep, and it actually creates a bending curve. Okay, so that's how you're going to know that. So, and also just a nice little fast way to memorize the fact is the fact that we did the opposite of this thing the other day, and we saw that the derivative of parabolas always gave us straight lines. Therefore, the integration of a straight line should give us a parabola. You can do the same thing on the left side of the graph. You know, you could put some y values on here. Like down here, you'd see that it's negative 5, so it's going to be a really negative slope on f. And then here at 0, it's going to be negative 3, so a little, well, I guess we should do this one. Then it's negative 4, a little less steep, and then here it's a little less steep, and then here a little less steep, here, and then finally when you get to 0, it gets flat again. So it's getting closer and closer to 0, so the line becomes less and less steep. But anyway, so that's why it's kind of important to be able to pay attention to the details a little bit. But the basic idea is when f prime is positive, f is increasing. When f prime is negative, f is decreasing. And when f prime equals 0, we have a horizontal tangent line. Okay. So let me give you guys one. Oops. Didn't want to erase all of that. Okay, so here's another one for you guys. Go ahead and give this one a shot and see what you guys get. When you unpause the video, I'll show you my solution. All right, once again, the height of your graph does not matter, just the shape and also where the smooth curve top or bottom is located. So, for instance, I see that to the left of negative 3, I have a positive slope because f prime, well, let me say that again. To the left of negative 3, f prime is positive because it's above the x-axis, which means that for f, to the left of 3, it's going to have a positive slope, so it's going in an upward direction. I also see that to the right of 3, f prime is below the x-axis, therefore to the right of 3, f should have a negative slope, or it should be decreasing, going in a downward direction. Next, we see that f prime touches the x-axis at negative 3, which means that f should have a flat horizontal slope at that point. Now, in case you guys haven't noticed, any time f prime touches the x-axis, that could be indicating that you have a relative extrema, right? Because when f prime equals 0, that's a critical value. So when your graph of f prime touches the x-axis, that's a critical value. So it could be a relative min or a relative max. In this case, it's a relative max because the slope goes from positive to negative. So in other words, when you're looking at the graph of the derivative, if it goes from above the x-axis to below the x-axis, then that point is a relative max because your slope goes from increasing to decreasing. But if it's the opposite, like the example I gave you guys earlier, then it will be a relative min. But let's look at an interesting situation here. Actually, I think I'll save that one for later. Let's go back and let's take a look at a third scenario now. All right, so let's go ahead and take a look at this. What if my f prime looks like that? It's a parabola. Well, the questions pretty much stay the same. Here we go. So I see that f prime is below the x-axis to the left of negative 2. So I see that to the left of negative 2, since f prime is below the x-axis to the left of negative 2 there, that means that it's negative. And when f prime is negative, that means that f is decreasing. So until I get to x equals 2, I'm going to stop there because that's where x equals negative 2, f should be decreasing. But then I see that at negative 2, f prime equals 0. So at negative 2, I should have a flat slope. To the right of negative 2, I see that, well, actually, to the right of negative 2 and to the left of 4. So in between negative 2 and 4, I see that f prime is above the x-axis, which means that f is going to have a positive slope between negative 2 and positive 4. So now f is going to start going in an upward direction until I get to 4. Now at 4, f prime is touching the x-axis. And when f prime is touching the x-axis, that means it equals 0. And when f prime equals 0, that means that f has a flat or horizontal slope. Finally, to the right of 4, f prime is below the x-axis, which means that it is negative. And when f prime is negative, f is decreasing. So to the right of 4, it's going to be decreasing. Now, I'm just using straight lines here, but they're going to be curved, just so you guys know. All right. So now that I've got a nice little sketch of what it should look like, I can come over here and draw a little bit better of a line. It's probably going to look more something like this, a nice smooth curve, where you have a relative max at 4 and a relative min at 2, because that's where f prime equals 0, critical values, and it's changing from negative to positive, which indicates a relative min, negative slope to positive slope, negative slope to positive slope. And at 4, we're changing from a positive slope to a negative slope, or from a positive slope to a negative slope, above to below. All right, but either way, that's what it would look like. All right, so notice how I just started on the left side of my graph, and I just kept asking those questions, okay? Okay, to the left, I see over here, f prime is below the x-axis, which means it's negative. What does that tell me about f? Make a sketch. And keep doing that as you go along. You're looking for 3 things: where it's below, where it touches, and where it's above. Where it touches and where it's below, and so on and so forth. So just keep up that process, and every piece you do, add a new part to your graph. Okay, so here's 2 problems here. Go ahead and pause the video and try number 1. Unpause the video and check your solution. And then I'm going to have you pause the video again after that and try number 2, and then you can check that solution. So let's start with number 1 here. Pause the video, try number 1, and then when you unpause it, I'll have my answer up here for you. Okay, so here's the answer to number 1. You guys check that. F prime is above the x-axis in the green highlighted region there. So when you look at the graph of f, the green lines are increasing lines. They're going in an upward direction as we move from left to right. The pink section is where f prime is below the x-axis, indicating that it's negative. And therefore, on the graph of f, we have f is on a downward slope at that point. Finally, the blue dots on the graph of f prime, where it touches the x-axis, indicates that f prime equals 0 there. So since the derivative is 0 at those 2 points, 0 and 5, that's where the graph of f is going to have some relative extrema probably. In this case, it does. At 0, it has a relative max, and at 5, it has a relative min. All right, so go ahead and try number 2 over there. And when you unpause the video, you'll see the solution there as well. And once again, guys, remember the height of your graph doesn't matter so long as it has that W shape and you have a relative max at x equals 0 and a relative min at 5 and negative 3, then you've done it correctly. So you should have a W shape with a relative min at negative 3 and at 5 and a relative max at 0. Okay? Now just an interesting question, food for thought. Looking at this graph of f, where would you say there's a point of inflection? Remember, a point of inflection is where the concavity changes. Remember how we said it's in between the peaks? So maybe right here, because to the left of that, that looks like concave down. And then to the right of that, it looks like it's concave up, right? So I would say that there's probably a point of inflection like somewhere right about here. And that happens at about x equals 3. Now I want to come up here to our graph of f prime and look at what happens here at f prime at 3. Well, what's significant about that point on f prime? It's a horizontal tangent line. So it looks like f prime has a 0 slope anytime f has a point of inflection. A point of inflection is where the second derivative changes from concave up to concave down, and it's usually when it equals 0. So the slope of f prime, which is f double prime, is 0, or in other words, f prime would have a flat slope at that point. So that might be stretching your brains a little bit much. It's kind of I don't know about for you, but this sometimes warps my mind trying to think about 3 different things at the same time. But just trying to give you guys some ideas here and rev your minds up for some information. So let's go ahead and I'm going to throw on a couple of not so necessary, but real quick worth talking about things. All right, so let's take a look at this one. This one's a little bit interesting. Here we go. So to the left of 3, we're above the x-axis. So since f prime is above the x-axis to the left of 3, that means f prime is 0. I'm sorry, f prime is positive to the left of 3. And when f prime is positive, that means to the left of 3 that f would be increasing. So my graph is moving in an upward direction until I get to x equals 3. And then what happens at x equals 0? I'm sorry, x equals 3. At x equals 3, my f prime is touching the x-axis, which means that f prime equals 0. And when f prime equals 0, that means that f has a flat slope at that point. And then what is happening to the right of that dot? To the right of that dot, it's a highlighter here. To the right of x equals 3, f prime is positive. And when f prime is positive, that means that f is increasing. And once again, you want to connect these with some smooth curves. So really, f's not going to look like this so much as it would probably look more like this. Okay? It does need to get kind of flat here, though. There we go. Because it has a flat slope at 3. But I want you guys to notice something. This is not a relative min or a max, even though f prime touches the x-axis. And why is that? Because f prime didn't change from positive to negative or negative to positive. It went from above the x-axis to above the x-axis, which means that f prime stayed positive. So the slope of f never stopped being positive. Okay? So that's another scenario that you want to be ready for. All right, I'm going to stop there with the f prime graphs. There's a few other little details we could talk about, but I don't want to make your guys' video go too long, and we want to just focus on the essential stuff here. So we'll let those other topics go. Maybe we'll throw them on at the end if you guys want to watch a little more. But for now, let's move on. Let's talk about the other half of our lesson, which is sketching, looking, what does the graph of f prime tell us about f? So once again, pause the video here, and when you unpause it, I'll go over the answers to these blanks. See if you guys can find the answers to these blanks. All right, so if f double prime is positive, that means that f is concave up. If f double prime is negative, that means that f is concave down. And if f double prime is 0, then f is a point of inflection. But we need to add more to that. So if you got point of inflection, give yourself a pat on the back. But it has to do more than that. It can't just equal 0. F is a point of inflection if f double prime changes from plus to minus at that point. Okay? So yes, we start by looking for where it equals 0, but it's only going to end up being a point of inflection if the second derivative changes from being positive to negative at that point. Okay? If it doesn't change from positive to negative, then it's not a point of inflection, because a point of inflection is where the concavity changes. Now that usually happens when f prime double prime equals 0. It doesn't have to, but it usually does. And since it doesn't always happen, we got to make sure that, okay, we start by looking for where it does equal 0, then we double check to make sure that it actually changes signs there. If both of those criteria are met, then yay, we have a point of inflection. Okay, so let's go ahead and take a look at some examples for that sort of stuff. We're on example 5 now. All right. So given that this is a graph of f double prime, we want to sketch a graph of f. All right. Now, what do we know, or what does this graph tell us about f double prime? And the question is the same as last time, okay? Positive means above, or actually, I should probably say it the other way. Above means positive, below the x-axis means negative, and on the x-axis means 0. So what do we know about f double prime when looking at this graph? Well, I see that it's always below. It's always below. Okay, great. So that means that f double prime is always negative for this particular function. Well, what does that tell us about f then? If f double prime is always negative, then that means that f is always concave down. So what does a graph look like when it's always concave down? It looks like a parabola. And once again, we really don't know how high up or how far down this graph is. All we know is it looks like an upside down parabola. That's it. Okay? Let's throw a student practice at you guys and see how you do. So see if you guys can sketch a graph of f from this. When you unpause the video, I'll share my solution with you. All right, there you go. So what do we know about f double prime? What does this graph tell us about f double prime? Well, since the graph is above the x-axis, that means that f double prime is positive. What does that tell us about f then? Well, if f double prime is positive, that means that f is concave up. So you have an upwards facing parabola. And once again, we have no idea the height of this graph. It could be higher or lower. We don't know. All we know is that it's an upward facing parabola. Let's do another type. All right. Let's go ahead and try to sketch a graph of f when our f double prime looks like that. So from this graph of f double prime, what can we tell about f double prime? Well, I could see that it's below the x-axis until we get to 4. I could see that it's above the x-axis after 4. And I could see that it's on the x-axis at 4. So let's do this one piece at a time. To the left of 4, f double prime is this graph is below the x-axis, which means that f double prime is negative. So what does that tell me about f? Well, that tells me that to the left of 4, my graph is concave down. So I have a graph that looks like this to the left of 4. And I see that to the right of 4, the f double prime graph is above the x-axis, which means that the second derivative is positive to the right of 4. Now, when the second derivative is positive, what does that tell us about f? Well, that would tell us that f is concave up to the right of 4. So to the right of 4, I'm going to have my graph bending in an upward direction. Finally, f double prime touches the x-axis at x equals 4. So what does that tell me about the graph of f? Well, if f double prime touches the x-axis at x equals 4, that means that f double prime equals 0. And we said that so long as it's going from concave up to concave down at that point, then that must be a point of inflection. And in this case, it is a point of inflection because we're going from concave down to concave up at that point. Now over here on this graph, you can tell it's a point of inflection because it goes from below to above. Okay? Now, an exception to that would be if you had a graph that looked like this. Let's say your second derivative touched the x-axis, but it stayed below. It went from below to below. In that case, it's not changing concavity at that point. In that case, that would not be a point of inflection. All right, so here's your second derivative. See if you guys can sketch the graph of f When you unpause the video, I will show you my solution. All right, there you go. I've accidentally put f double prime up there, just f. So if f double prime is above the x-axis to the left of 1, that means f double prime is positive to the left of 1. I'll indicate that. So since f double prime is positive to the left of 1, that means that the graph of f would be concave up to the left of 1. And f double prime is below the x-axis to the right of 1, and therefore that means f double prime is negative to the right of 1. And when f double prime is negative, that means that f is concave down. So f will be concave down to the right of 1. Last, since f double prime is touching the x-axis at 1, that means that f double prime equals 0 at 1. And if f double prime equals 0 at 1, and we're changing concavity, which we are because we're going from above to below, then that would indicate that at 1, f should have a point of inflection where the concavity is changing. Okay, so I'm going to give you guys another one to do. Just a second. So go ahead and try this one. Here we have f double prime again. See if you guys can sketch a graph of f based on this particular second derivative. All right, so to the left of 6, we have a green region here that is below the x-axis, which means that on that region, f double prime is f double prime is negative, which means that f is concave down to the left of 6. To the right of negative 6, f double prime is above the x-axis, which means it's greater than 0, which means that f is concave up. And that's going to happen until we get to 2. So in between negative 6 and negative 2, we have a concave up graph. And then to the right of negative 2, we're back being below the x-axis until we get to 3. And when f double prime is below the x-axis, that means it's negative, and therefore, until we get to about 3, we're going to be concave down. Now something interesting happens here. It equals 0, but it's still concave down after that. So I put a little wobble in there, but it didn't change concavity. We still went from concave down to concave down. Concave down to concave down, and it just kind of became 0-ish there for a second, but it wasn't enough to flip it upside down. So it's like it was trying to get to, it's like going from concave down closer and closer to 0 so that it could make it to concave up, and darn it, it didn't make it. It kept being concave down. So on this graph, it's like concave down, closer and closer, trying to bend in an upward direction, but now we're going to keep bending in a downward direction instead. So that's just kind of how I drew it. Now, if you didn't include this little wobble, it's okay. You didn't have to. It's fine. It would probably be good enough just the way it is. But in this case, this is an example of one that would not be a point of inflection. Okay? These two are, because the concavity actually changes. And you can see that on this graph over here because it actually crosses the x-axis. But here, since that one does not cross the x-axis, that is not a point of inflection. And just real quick, I'll go through some other types of examples with you of some not as important details, but just things to kind of develop your thinking on the matter a little bit deeper. Okay? So we talked about horizontal asymptotes, right? Well, it's interesting. You know, the rule we learned when we were going from f to f prime was to the left it stays the same, and to the right it flips. Well, an interesting fact of the matter is the same thing happens when you work backwards. In other words, to the left it's still going to look the same, and to the right it's going to flip. Okay? So the rule actually doesn't change when it comes to vertical asymptotes. All right? Let's talk about this next one. Now, we saw this situation happen. You guys remember what kind of shape that made? Well, let's see if you can figure it out. First of all, to the left of 3, f prime is constantly equal to 2. So if to the left of 3, f prime is constantly 2, that means to the left of 3, this graph constantly has a positive slope of 2. So let's just start here, because it doesn't really matter where you start. We're going to go rise 2, run 1. So my graph is constantly going to have a slope of 2 to the left of 3. To the right of 3, f prime is below the x-axis and it's negative, but we could be more specific and say to the left of 3 it's constantly negative 2. So to the left of 3 it's constantly got a negative slope of 2, which will look like this. So it's going to give you a V shape, right? But there's one thing here. Notice the open dots? Well, that means that the function is not differentiable because the derivative doesn't exist there. But does that mean that it's not continuous? Not necessarily. It could be an open dot, or it might not be. It could be filled in. We don't know if that point exists or not. Because if a function is differentiable, then it's continuous. But if it's not differentiable, then that doesn't mean that it's not continuous. It could be. We've seen functions that are not differentiable, but they are continuous. So we're not sure if that dot there actually exists or not. They would have to give us more information. Furthermore, we actually don't even know if it makes a V shape, although that's what we're used to seeing from our previous lesson. Let me show you something else, though. All we know is that to the left of 3, it's a positive slope, and to the right, it's a negative 3. So who's to say that it's not got a negative 3 slope starting down there? We have no idea. All that we know is that to the left of 3, it's got a positive slope, and to the right of 3, a negative. So we really don't know. Now, sometimes they might say, graph f if you know something. If f of 3 equals 2. Well, now, right there, then you know that that point exists because they told you. And they might say, and f is continuous, in which case it wouldn't be a jump anymore. They would have to connect. So they might give you more information to get a V shape, but you really don't know. All you know is that to the left, the slope is a positive 2, and to the right of 3, it's a negative 2. So you're kind of up in the air there with doing that kind of stuff. Now, this next one here is kind of interesting. Notice, by the way, we're not talking, I hope you guys have noticed this. I should have said at the beginning. I'm doing problems like at the beginning of today's lesson. These are not second derivatives. These are first derivatives. So we're just talking about slopes now, right? We're not talking about concavity. All right, so let's take a look at number 3. Well, what do we know about this slope? Well, it looks like it's always positive. So if the slope is always positive, you're going to think, aha, I know how to do that. F is always positive. There, ha. Well, the problem there is that what would the derivative of this kind of a line look like? That derivative would look like, yeah, it would always be above the x-axis, but it would look like a flat line. This thing's bending. Okay, so what the heck do we do with that? So we know that f is always increasing. That's cool enough. F is always increasing, and we know that because f prime, which is the slope of f, is always above the x-axis, which means it's always positive. And when f prime is positive, that means that f is always increasing. So we know that no matter how we want to draw this graph, it's always got to be moving in an upward direction somehow, but it's not going to be a straight line. So this is where the devil is in the details, okay? So let's get some numbers on this graph up here. All right, so let's pick way out here at this point. What does f prime equal there? It's probably just a little bit less than 1, so we'll say like 0.5. What about like right here at 3? It looks like it's maybe like 1.5. Now, where am I getting these numbers from? Remember, this is the graph of f prime, so I'm asking what's the height of these points. So this point here is about 0.5 off of the x-axis. This one's about 1.5 high. How about right here at 2? Well, now we're at 4. And how about right here at 0? Well, now we're at 5. And it's symmetrical, so it's going to do the same thing on the other side. So let me just copy all that. So it's going to be 4, 1.5, 1.5. So those are the heights of those points. So f prime is 0.5. So when I come over here to my graph of f, when I'm at x equals 6, I have a slope that's 0.5. So it's a positive slope, but it's a little bit flat. So I'm going to draw a little bit of a flat slope. And then when I get to 1.5, it's a little bit steeper now because it's higher, right? So it gets to be a little bit steeper there until let's keep going until we get to 2. Now it's getting even steeper. And here it's getting even steeper. And now here it's a little bit less steep now. A little less steep. I think I went a little too fast. Let me back up a bit. So really steep, and then a little less steep, a little less steep, and a little less steep. This graph is always concave up. I'm sorry, not always concave. It's always increasing. But as you guys can tell, when you look at the details, like what would the slope be here? In other words, how high off the x-axis is it? Well, it's about 0.5, 1.5, 4, 5. And then you can kind of sketch slopes that get steeper and steeper, and then just follow the steepness based on the y values of the f prime, and you can kind of get some ideas there. So I do try to keep it simple, where I just look at above, below, and on the x-axis to tell us whether we're sloping up, down, or flat. But sometimes it's nice to be able to break it down and actually look at what the slope values are at those points, and then roughly sketch what's happening with the slopes on each interval. Okay, so let me see here. So the first two I showed you, not a big deal. I'm not too worried about those, but I want to let you guys try one of those last ones that I just did, a little bit tougher. So let me sketch you guys a graph here, and let's see if you guys can sketch the graph of f. And this is going to be a graph of f prime, mind you. Okay, so it's going to go like this. See if you guys can figure out what that derivative would look like by doing the same thing I just did. Picking a couple of y values on this graph and translating those as slopes with their relative steepnesses for a graph of f. When you unpause it, I'll show you my solution. So I picked some various points along this curve. Here the y value is about 0. Oops, I didn't want to do that. Here the y value is pretty close to 0. It's not quite 0, but it's really close. So I'm just going to pretend it's like 0. Here the y value is 1 and 3 and so on. So I just went through and picked a few points and got their corresponding y values. Now when f prime is 0, that means f is flat. So f is going to be flat right about there. Here, f is going to be increasing. And then here, f is going to be increasing again, but a little bit more steeply because it's a bigger number. Here, f is going to still be increasing because it's positive. The slope is positive. F prime is positive, therefore f has got a positive slope, which means increasing, but it's not as big of a slope as this. So it's a little bit flatter. And then here, the slope is flat again because f prime is 0. Here, the slope of f is going to be -1. I've got all my signs wrong down here. So a negative slope might look something like this, right? And then it's more steep at this point, less steep at this point, and then flat again here. So we can kind of see, based on those, the y values of f prime indicate the steepness of the slope for f. So let's do that really quick. All right, so here we go. Way over here at x equals -12, I have a really flat slope. So I'm just going to draw a flat line here. Doesn't matter how high up I do it. I could have drawn it up here, but it doesn't matter. So I'm just going to give it a flat slope until we get to our next point, which is at -4. So flat slope until we get to -4. Now at -4, it starts to curve in an upward direction a little bit until we get to -2. And then at -2, it curves up even more until we get to about -1. At that point, it starts being so steep at -1. So it starts to flatten off a little bit. And then finally here at 0, it's actually a flat line. So this is what it looks like so far. All right. Now we've got a negative slope at 1. So it's going down a little bit here at 1. And at 2, we have a even more negative slope, so it's a little bit steeper at 2, so it's going down sharper. At x equals 5, we're back to a less steep slope, so it starts to get a little flatter, and then finally way out here in the end it gets flat again. There you go. So it looks something like that. All right. So you can basically just find various y values along your derivative graph and interpret those as steepnesses of slope to find your f graph. So those are some a little bit more specific problems. These last 3 types of problems I went over with you, they're not very commonly asked, but they're great ways just to take the basic concept, which is summarized in these tables I gave you guys earlier, this one and this one. These tables, those 2 tables are really your most important pieces of information. And the main examples I gave you. But those last 3 is just to further your thinking a little bit. Not quite as important, but it's good to further your thinking and develop the concept a little more by looking at those. But anyway, I'm going to stop there and let you guys hit up your homework, and we'll see you guys in class.